is your Bessel equation, for instance. I believe 1 over rho partial. This is the Bessel equation in the complete. All the solutions with the correct boundary conditions are complete. So all modes in a waveguide are complete, for instance. Okay, you can expand anything inside the waveguide in terms of those modes. And what else? And in terms of the any Sturm-Liouville problem, not just these two I have given as an example here. It can be Legendre's polynomial, it can be Legendre's function, it can be the Gauss-Legendre function. And all those functions are complete because they all belong to this class of Sturm-Liouville problems. Okay.
So all complete solutions are orthonormal.
They can be made orthonormal. They can be made orthonormal, and then in the limit, when you make the space expansion very, very large, they become orthogonal in the sense of the delta function. Otherwise, they can be made orthonormal in the sense of the Kronecker delta function. This is called the Kronecker delta function. Okay, they can make orthogonal in that sense. So, any more questions regarding that derivation? That derivation, that identity is a very important identity. And if I write it down properly, I will get the fact that e to the I k naught r over r, a spherical wave, can be written in terms of, this gives me 1 over 8 pi cubed times pi I. And then if I further multiply by 4 pi, okay, the pi square, I, and then I get I over 2 pi. Okay, the constant becomes just I over 2 pi, actually. dkx, dky, e to the I kxx plus I ky y plus I k naught z z, and then over k naught z. Let me see if I get this constant correct. Okay, it's I over 2 pi. This is called the real identity. So derived about 1919, so maybe about 50 years after Maxwell's equation. Maxwell's equation was completed in 1864. So by the time we reached 1919, people came up with this real identity. So why is this that useful? So let's try to elucidate some physics out of that. This is just a simple statement that if you have a spherical wave, you can write it in terms of the expansion of plane waves. And what directions are these plane waves propagating? Well, this direction is a point source. This is the z direction. This is the x and y direction. What it says is that this thing over here is an outgoing wave for z larger than 0. Okay, so this corresponds to plane wave propagating in all directions upward when z is larger than 0. But when z is less than 0, if z is less than 0, you have to replace it with a minus sign, right? And if you look at this plane wave expansion again, they are all plane wave propagating in the downward direction. Okay? So a physical picture of the plane wave will look something like that. But what's more is that what happens if kx squared, you're integrating over the kx and ky plane on the complex kx and ky plane. If kx squared plus ky squared is larger than k naught squared, remember k naught z, as you see before I erased that, k naught z is equal to k squared minus kx squared minus ky squared. What happens if kx squared plus ky squared is larger than k naught squared, you get evanescent wave, right? This wave will become evanescent because it starts to decay. I cannot draw the picture like this anymore. These are for propagating plane waves. So when you integrate over the complex plane, kx and ky plane, inside this circle, which has a radius of k naught, you get propagating wave as you integrate. But outside the circle, you have propagating. Outside you have evanescent. Okay. Outside the circle, you have evanescent wave. Why are the evanescent waves important? They are outside the circle on the kx and ky plane. What does that signify to you? What is the significance of that? That the evanescent wave are outside the circle and all the way to infinity. With the kx and ky going to infinity, they are all evanescent waves. What is the significance of that?
They contain high frequency content.
Right, all the high frequency content are contained in the evanescent wave. Very good, right? So if you look at this as a Fourier transform integral, kxx plus kyy, this is nothing but a Fourier transform integral. What it says is that the high frequency component of this Fourier transform, when kx and ky are large, actually correspond to evanescent spectrum of this thing. So if you have a point source, what it says to you is that if I have a point source, okay, say this is my z direction, this point source produces a singularity here, and if I were to take a cross section of the field here, it will look something like this maybe, very sharp and going to infinity, right where I see that, and then oscillate around it. I get a nice singularity there. But if I were to look at this field, this produces a spherical field that oscillates. By the time I reach here, I take a cross section over here, or maybe slightly further away, so that it wouldn't collide with this picture that I'm trying to draw. You get an oscillation, but then the singularity gets smoothed out, right? Gets smoothed out. And then if you go further away, you might just see something very smooth. Okay. Maybe still some oscillation, but rather smooth. So what it says is that in order to see the singularity of this field, you have to be close to the source. And if you're close to the source, z is small. If z is small, the evanescent wave decays less. And as you're close to the source, you can pick up more evanescent waves. But if you're far away from the source, you pick up less evanescent waves. So that would be the physics of all point scatterer. Say if I have a whole bunch of point scatterer, if I send in a plane wave coming in, the plane wave is very smooth, but the time when it hits those point scatterer, it produces a lot of point sources. These point sources will re-radiate. And each of them will re-radiate like this function over here, like a small spherical wave. Okay? And they will produce both propagating and evanescent waves. But the evanescent wave, if you're outside and at a small distance away, you will not see the evanescent wave. You will only see the propagating wave. In other words, you only see the low frequency component of the scattered field. You will not see the high frequency component of the scattered field. Does everybody get that? Okay, there's one more very important physics. So if you understand this physics, you can do something called NSOM, or SNOM. SNOM stands for Near Field Scanning Optical Microscopy. And this is the European way of saying it, which is scanning near field optical microscopy. Okay. Okay. So what you can do then is that if you want to have a very high resolution image, of a surface. You send in an optical plane wave, okay, and some of this might be very, very small features. You can think of them as point scatterers now, and the wave is scattered in all directions. As point scatterers, they produce evanescent waves, and if you want to measure the high resolution image of this surface, you have to put your probe very, very close to the surface, maybe a fiber probe. Okay, you put an optical fiber with a very refined tip. You sharpen the tip so much that this optical fiber probe will pick up some optical field very close to the surface, and you scan this optical probe on the surface to pick up the evanescent component. And that will give you a very highly resolved image of the surface, much more resolved than what you can achieve with the Rayleigh limit. Yes?
Why doesn't the evanescent wave decay?
But you put the probe very close to the surface. The evanescence wave, if you think of the physics here, where the wave comes in, induce a lot of sources. These sources, some of them can be very small, correspond to point sources. The point sources will irradiate. They will produce evanescent and propagating wave. If you're observing over here, you only see the propagating wave. You'll see only the signal inside this circle. You will not see the field from outside this circle. Hence, you have a washed out image of the field, and you will not have a high resolution image of this. But if you put a scanning probe very close to the surface, you'll pick up things that are outside this circle. You pick up some of them, and then it gives you a highly resolved image of the surface. That is called the near-field scanning optical microscopy. Okay, there's one insight you can gain just with this formula. There's another insight you can gain, which is that if you want high-resolution image, you need to put your observation point very close to the source. So of course, then people think about this crazy idea of metamateria, double negative index material. So that if you put a point source over here, it's a negative reflection material. It turns out that mathematically you can prove that when the evanescent wave from this source reaches this thing, the evanescent wave, say, decays in this fashion, and then it will grow in a double negative material. This is called the double negative material. DNG is a notation that you like in it. They say that since it grows, mathematically it grows. So if you put your observation point over here, you can actually see a very highly resolved image of this point source. That's what people claim. But it's extremely difficult to do because it's extremely difficult to amplify exponentially small fields. Okay, by the time the evanescent wave reaches here, you need to amplify with this crazy thing, double negative material, okay, and make it grow. And it's very difficult to do. So they can do with some limited enhancement of resolution, which maybe they can pick up some evanescent wave from slightly outside this circle. That's about it. Okay? You can also do a lot of clever things. You can also try to measure this optical field in here and then extrapolate outside the circle. That will give you some kind of enhanced resolution. And if you study the resolution, that is, if you have an object, say two objects, okay, if you have a wave coming in, and then say they're small compared to wavelength, it will produce propagating and evanescent spectrum. And then you ask yourself, if I were to observe these two objects over here without any fancy equipment, I will reach what is called a Rayleigh limit. Okay, because what I would get is that I will have only the low-pass filter version of the scattered field. I can only observe inside this circle. And if you look at the scattered field from this object, it will not truly having all the information about this scatterer. So when these two scatterers are about, I think lambda over 4 or lambda over 2 apart, they cannot be resolved. That's called the Rayleigh limit. So we have 2 point scatterers. If you look at the optical field from them, if they're less than maybe lambda over 2 apart, they become very fuzzy. It's because of this formula. You can explain it all by this formula as well. Okay? They're really limited. Because when you put your eyes over there, without any aid, without any microscope or anything, you don't pick up any field. Okay? And you will have to really limit. But this formula also tells you something very interesting. It says that if I have a point object over here, it will produce propagating wave. Okay, propagating wave. And then the wave will be propagating until it reaches a grazing angle. What is beyond the grazing angle? So this will be propagating wave in all directions. What is beyond the grazing angle? Beyond the grazing angle is evanescent wave, right? Beyond the grazing angle is evanescent wave.
Why doesn't the wave propagating beyond?
Oh, they have some over there too. Okay, I just didn't draw them. Okay, you want me to draw them in? I'll draw them in. Okay. So, but beyond the grazing angle will be evanescent wave, right? That's what it means. If you look at this, K0z becomes 0 right at that circle. K0z is 0 on that circle. Okay? K0z, this is z direction. K0z is 0 in that circle means that the wave vector that corresponds to that plane wave must be horizontal or grazing. Right? Beyond grazing, the wave propagates in all directions, but the moment they go to horizontal, beyond that, the wave is evanescent. Okay, this gives you another interesting insight, which means that if I have a telescopic lens over here, if I put the telescope over here and try to collect the wave field from that point source, I will only pick up those propagating mode inside this angle theta. Okay, which means that I actually do not pick up the whole circle. I pick up only propagating spectrum from inside a certain smaller circle than the maximum possible. Okay? And then I do some Fourier transform, Fourier inverse transform. And then try to reconstruct the image here, the point source over there. Would this point source be an exact replica of that point source over there? No, right? Because I only pick up that much Fourier data. And hence I cannot refocus to a perfect point source. This is what the lensing system does. The lensing system cannot reproduce an exact point source for you. It only picks up the low-pass filtered version of the optical field and try to refocus. And no matter how hard you try, you can only use the information from there to get the point source. Okay? So what do I do if I want a higher resolution telescope? What do I do? I make the lens bigger, right? I make the lens bigger. Then it will pick up more and more circle, but I cannot make it very, very large, infinitely large. Then I'll pick up a full circle. And if I make it small, then my resolution is no good. So when you go and buy a camera, you look for the one with the big lens. You know why, right? You want a big lens so that you pick up as much Fourier data as possible. Okay? As much Fourier data as possible. And then you try to use that big lens, collect as much high resolution information as possible. What about digital zoom? Let's talk about digital zoom. Okay? So you came up with a small digital camera with a small lens. So you cast an image on your film at the back, and then you try to make this image bigger by magnifying this thing over here. Is that a good picture? No, right? It's no good picture. So if you have an object that's far away, you take it with a digital camera. You think you have a good camera, so you zoom in, make it very big, and take a picture over there. It's no good. So if you want a sharper image of this object, what do? You move your camera to as close as possible to the object. Okay. Then this angle that you obtain, this theta becomes bigger. Right? And you pick up more Fourier data, and then you zoom into your lens. Your image will be better. So next time when you have a digital camera, don't get fooled by it. In order to get a high resolution image with the digital camera, move as close to the object as possible. Okay, move as close to the object as possible, so that you pick up as much Fourier data as you can. Okay? Does that make sense? Okay, good. So that is so much about the whale identity. Let's take a 5 minutes break.